Hello and welcome to this video. In this video, we will solve exercise 44, 45 and 46 from chapter 2 from the book Contemporary Abstract Algebra 10th edition by Joseph A. Gallian. Okay, we start with question 44. Let R alpha and R beta be rotations in dihedral group Dn. R alpha mean the rotation with the angle alpha and R beta mean the rotation with the angle beta. And F be the reflection in dihedral group Dn. What rotation is Fr alpha, Fr beta and Fr alpha, Fr beta F? Means we have to show or we have to find what kind of rotation these are or what are these rotation by angle. Okay. Since we know that Fr alpha is equal to R minus alpha into F, and similarly Fr beta is equal to R minus beta F. These identities or this identity is proved in question 43. You can see. Okay. Now consider that F R alpha, F R beta, and that can be written as we apply the identity on this one. We got F R minus alpha R beta. Okay. The F and F, the product is identity, and we remain with R minus alpha R beta, and that is R beta minus alpha. So this rotation, this one is actually rotation with the angle alpha minus beta. Oh, sorry, beta minus alpha. And now we consider second one, R alpha F, R beta F, and we apply the identity on these two elements. We get R alpha, R beta minus beta, F and F, and the product of F with F is identity, and we remain with R alpha, R minus beta, and this is actually rotation with respect to the angle alpha minus beta. So the first rotation is with angle beta minus alpha, and the second rotation is with the angle alpha minus beta. Okay, we move to the question number 45. The statement is prove that if G is a group with property that the square of every element is identity, then we have to show that G is abelian. Okay, let A and B are any arbitrary elements of G, and since every element of G as square is equal to identity, so if AB belongs to G, it means A square is equal to identity and B square is equal to identity. Now consider AB, because AB both are elements of G, then their product is also element of G. And since AB belongs to G, it means AB whole square is also equal to identity by the definition that every element of G has square is equal to identity. This can be written as AB is equal to E. If we pre-multiply both sides with A, and this is A square, But we know that A square is identity, so this is equal to BAB. And similarly, if we multiply both sides, pre-multiply with B, and this this is B square, and B square is identity, so AB is equal to BA for all AB belongs to G. And this means G is a billion because AB is equal to BA for all AB belongs to G. Okay, we move to the next question. The question number 46. The statement is that in a finite group show that the number of non-identity elements that satisfies the equation x to raise power 5 is equal to identity is a multiple of 4, means the number of elements which satisfy this equation are actually multiple of 4. And if the stipulation that the group be finite is omitted, the condition of finite group is omitted, what can you say about the number of non-identity elements that satisfy the equation x raised power 5 is equal to identity? Let's start the solution. Let S be the collection of those elements of group G such that their if we take their power 5 we get the identity. Now we have to find the cardinality of this S, but as we have to find the number of non-identity elements, so we consider T is equal to S minus the identity element. Now we want to show that the cardinality of this set T is multiple of 4. Okay. If x raised power 5 is equal to identity, then order of x must be less than or equal to 5, because order is the least positive integer which satisfies that x raised power that number is equal to identity. And if x is giving identity with the power 5, then it is clear that the order of x will be less than or equal to 5. Since x is not equal to identity, non-identity element, so the order is not 1. This is clear. And if order is not 1, so it is exactly 5. And why it is exactly 5? Because 5 is prime and not divisible by 2, 3 or 4. We know that whenever any element give identity on, if we take any its integral power, then that integer will be multiple of its order, because 5 is not the multiple of 2, 3 or 4, and 5 cannot be 1. So the order, and x is giving x raised power 5 is identity, so the order of x is exactly 5. Okay, so for any x belongs to T, the set generated by x will be E x, x square, x cube, and x4 is cyclic subgroup of order 5. We will study the cyclic subgroup or cyclic group in detail in the next chapter. Okay. It contains exactly 4 non-identity elements. We are actually talking about this set. This set contains 5 elements, but one element is identity. So it contains exactly 4 non-identity elements that are x, x square, x cube, and x4. Okay. All satisfy the given condition. We can check easily that a trace power 5 is E. A is any of these 4 elements. Okay. Now let y belongs to T. If this y does not belong to the set generated by X, we get other 4 non-identity elements because y belongs to T, so y to the power 5 will be identity. And the other 4 non-identity elements are y, y square, y cube, and y4 exactly in the same way as we have found by the set generated by X. Since group is finite, so we have finite such elements. So the cardinality of T is multiple of 4, and that is what we want to show. And if we omit the condition of finite set, finite group for infinite group, the same procedure or same argument will work, and hence the number of elements, non-identity elements with the condition x raised power 5 is identity are multiple of 4. And that's all about today's lecture. See you next time. Please subscribe the channel and like the video.